All right, let's talk about improper integrals with infinite discontinuities. Function has an infinite discontinuity if this happens. Let's translate this. If I approach some value, some x value on my function, I reach infinity or approach infinity or negative infinity, then I have basically a vertical asymptote. This is a infinite, I had a hard time saying it, infinite discontinuity. There's so many I words in here, improper, integral, infinite. Okay. So we have a few ways that we can work these out. If f is continuous on the interval from a to b and has an infinite discontinuity at b, okay, so we have a vertical asymptote, basically, at b, then we're going to have to approach b, we call it c, and then we're going to approach b from the left. And we have to do that because b is all the way on the right. So we have an interval from a to b. We have no choice but to come at this one from the left. Notice that notation. Well, maybe we have to approach something from the right. That would be the circumstance where we have this a on the left where there's an infinite discontinuity. And then we get into this situation where perhaps somewhere in between a and b, we have an infinite discontinuity. I'm skipping over some of these words in the middle. We'll come back to them in a minute. But we have an infinite discontinuity somewhere in between a and b. We would have to split this thing up into two separate pieces, and then we do these little parlor tricks with limits going one direction or the other. Okay? So f is continuous on the interval from a to b, solid a to b, closed interval, except maybe at some value c in a and b. And that is where the infinite discontinuity is. Then we would break it apart at that point. So let's just jump in with this first example. We're going to evaluate each of these integrals. Here's the first one. And what I want to do is just kind of stare at this and say, what can x not be? Oh, 0. So if you graph this, and we will for fun, if you graph this, we would do 1 over the cube root. I pressed math to get that. Cube root of x. And I want to graph it from 0 to 8, and we'll just do a zoom fit. So zoom 0. There it is. Clearly an infinite discontinuity. There it is. I wonder what I can do to evaluate this integral. Well, I can't do just like straight up fundamental theorem of calculus, because if I did, I'd have to plug in an 8. That's cool. Plug in a 0? Oh, what? How are you going to do that? So don't. What I'm going to do instead is the limit as a, why a? Because the screen just got blurry, that's why. Because that'll be a, that'll be b, and a is the forbidden number. A is where my infinite discontinuity is. So a is going to approach 0 from the right. It's this circumstance right here. Okay. Of a to 8, let's call it 1 over cube root of x dx, okay? It looks like a little plus sign there that leads to that, but it's not. I'm approaching 0 from the right. So let's keep going with this idea. We have the limit as a approaches 0 from the right of the integral from a, can't just plug in a 0, to 8 of x to the 1/3, but it was in the denominator. Good to know. There's that. We are going to proceed. The limit as a approaches 0 from the right. We're going to add 1 to this exponent. That gives me 2/3. And then 1 divided by 2/3 is going to give me 3/2. We're going to evaluate this at 8 and at a, and then subtract them. So we're using the fundamental theorem of calculus without ever having to plug in 0 into the forbidden place. So we're going to proceed. The big idea is behind us, actually. The big idea was, oh, I have an infinite discontinuity here. I'll call it A. Makes sense, alphabetically, A and B. And so I have to approach 0 from the right. That's my only choice. That's what's really going on. So I have the limit as a approaches 0 from the right of 3/2 times 8 to the 2/3, we can do that in our head, minus 3/2 a to the 2/3. Things are getting a little tricky there. We'll proceed. Fill up the whole paper, not really. The limit as a approaches 0 from the right. Wow, Okay, 8 to the 2/3. We're going to do some stuff in our head here. It's going to be fun. 8 to the 2/3. The cube root of 8 is 2. 2 squared is 4. Let's not do it in our head. Let's do it on the side. 3 halves, 8 to the 2/3. 3 halves, cube root of 8, and it's squared. 3 halves, cube root of 8, which is 2, squared. 3 halves times 4, which is 12 halves, which is 6. Okay? It'd be way too much to do without writing it down. So 6. Minus 3 halves. Oh, let's go ahead and rewrite this fraction just because we can. There it is. Okay, well, this limit only applies to things with the A in there. So 6 minus the limit as A approaches 0, using some properties of limits just without even thinking about it. 3 halves cube root of A squared. So basically what we're doing is evaluating a limit. Can I plug a 0 in here? Yeah, I think I can. From the right, well, sure. Actually, in this case, it doesn't matter, but I am approaching from the right. So I have 6 minus. Now, it looks like I'm about to just plug in a 0, but technically I'm approaching 0. But if I approached 0, then I would have a 0 here. The cube root of 0 is 0, squared is 0, times 3 halves, still 0. Final answer is 6.